So I'll present then my PhD thesis, what I've been doing so far. And the actual name of this is Tool Automation of Model-Based Design of Cyber-Physical Systems. And it's part of the Into CPS project, so actually it fits with the agenda of this Into CPS project, so I'll also mention what the Into CPS project is about and how this PhD fits inside this vision of Into CPS. Yeah. So just briefly, the agenda, first I will just describe, so everybody knows what a cyber-physical system is, and then I will describe how this Into CPS project approaches this development of these cyber-physical systems, and then I will end up just two of these contributions of this PhD to this Into CPS project, and I will end up in the end with just a brief conclusion of what has been done so far and what the plans are for the future. This both the PhD and the project itself. So first of all, cyber-physical systems are basically just systems where you have computers controlling physical systems. And I just put examples here of the Into CPS industrial case studies here. But in general, it can also just be an airplane or a car. It's basically every system where you have a computer or a processor described in software which controls some, like a physical system, let's say like a wing of an airplane or a robot arm. So basically it means such systems are very complex, and also it gives rise to some of challenges to developing such cyber-physical systems. And one of the key challenges in developing cyber-physical systems is that usually the control itself is usually described in a discrete event time, and then the physical systems like the movement of the robot arm or how our car actually moves is given by differential equations. So these are two different worlds, you can say, which are hard to simulate together. So if you want to develop a cyber-physical system, you actually need to look at both the control itself, which is described in one notion, and the physical part of the system, which is described in another notion. So some of the things that this Into CPS project actually wants to achieve is actually to support such a development of such systems that you can actually you actually don't need to realize the real thing before you actually can test how the controller works together with the car. We actually want to use models before we develop the real thing to see if it's going to, how it behaves together, both the software combination with the physical system. So yeah, just to give the overview of the Into CPS toolchain in this Into CPS project, it's a quite big project with not only Aarhus University but other universities across Europe and industrial partners, which also saw with the case studies we will actually apply our toolchain to. But the basic idea of this toolchain will be that we are able to go from requirements of cyber-physical systems down to perform some kind of co-simulation of different types of models, and I will go into details in the next couple of slides about this co-simulation approach. And then in the end we actually want to actually realize both the physical system and at the same time the control code. So this is just the main overview of this Into CPS toolchain. So just to highlight where this PhD will contribute inside this project, one part will be we will contribute to enabling co-simulation of different types of models. Like I mentioned before, we have different kind of notions inside a cyber-physical system. And we will look at how we actually can automate the process of when we have a software model to go down to the code. So first I will look at how we enable co-simulation of cyber-physical systems. This is just to give a brief motivation of why this can be a good idea. This is actually for a project before Into CPS, which Into CPS builds upon, called DESTEX. And you can see here, this is the model, and this is the real implementation of that model. So basically you can actually try different things in your model before you build it. And this is also this model is actually made with two tools combined. One which is used to describe the physical movement of this robot, and the other one is used to describe the control software. Yeah. So this is actually what we want to achieve, build upon this in the Into CPS project. And we actually want to do this by combining different tools, because our at least approach to solution to enable this simulation of such cyber-physical systems is not to develop a totally new tool that's able to do everything. The idea here is we actually want to combine different tools that already have proven good. Maybe one is good to describe software, the other one is good to describe the physical system, and we want to enable these to communicate together in order to perform a simulation together. So what we did here was to use something called the FMI standard. And the basic idea, so we didn't came up with the FMI standard, it's just we use it. It's just part of an industry standard. But the basic idea of this FMI standard is that each tool, if you have a tool, no matter what, it's used for either software modeling or physical systems modeling, when it's able to export such an FMU, then you know actually how you can control this FMU from the outside, how you can make it perform some kind of simulation. And we want to exploit this in order to enable co-simulation of a cyber-physical systems, or a cyber-physical system. Yeah, so this is just a bunch of more details about it, but this is the basic idea of the FMI standard. When we have this export, we actually know how we can make it do stuff. And also with respect to time, which I will show next. So the basic idea of this part, what we will do, is to develop a master algorithm. So we say these are already given, these two FMUs from different tools. And I'll give an example in the next couple of slides for a real-world example. But the basic idea is when we know how to get, if this is the master algorithm, we know how to get its output, because we say just they're connected, and then we can set it here, and then we can do another simulation. So this, yeah, you can just ask questions in the end if it needs to be clarified. But this is just, the key point is we are able to export something which we know how to communicate, simulate from the outside. And the contribution, what I participated with this PhD is we make such a master algorithm which is able to make such FMUs, which can be different models from different tools, to make a simulation together. So just to give an example how it could look like. It could look like you have something maybe described in software here, and you have two water tanks which needs to be controlled. So basically this will look like such a thing with FMUs, and then you can use this master algorithm that I showed before in order to perform a simulation to see how they behave together. So this is the thing I mentioned all the way in the beginning, is we want to look at it on a model-based level, all the models together, to see how they behave together, and not only to look at the control itself, look at these two themselves in their tools, and then just realize it and put them together to see how they work. So this is the idea, to enable the models to simulate and see how they behave together. Yeah. So basic, when we have such a model, and we have, okay, now we are happy how it is, and it fulfills our requirements. So the next part will actually be to go to the actual realization of such a system. And of course, I will not go into details of, because these, of course, you need to build physically. If, let's say, if it's a water tank, these physical systems, or a robot arm, you actually need to build that. But what we want also to support in this Into CPS project is, when you have developed such a controller with a software model, we actually want to support the automatic generation to a specific target with respect to our industrial partners currently. So the idea is, when you have performed a simulation, we actually want to map the same kind of behavior to the processor of choice. And of course, one of the biggest challenges here with respect to the realization of software is time, because software itself does not have time. In the software model, like let's say C++, does not have time by nature. it first gets introduced when you implement it on a concrete processor. So, and of course, but when you model and when you make simulations, you actually have time so you can see how it behaves. So, so this of course provides a challenge in the actual implementation. Yeah, so these are some of the challenges, and I don't have any results to show because this will be part of the next years of this project. But this is just a key idea of actually to supporting this automation of going from a model which you have validated and avoiding to re-implement the same model into something else and then make it execute. We want to automate this this model of the software. So you can also basically look at it. If we have an FMU that was part of a system, we actually are able to generate code to a specific target and then connect it to the physical thing or physical system and then make them communicate together. Yeah. So these are some of the challenges for code generation and what we want to support into CPS. So just to sum up and show a little bit more detailed picture of this into CPS, the key idea is that we want to support both this architecture model, so just based on some, let's say, a class diagram or just SysML diagrams to just show how the models are connected, and then we can have some of the cyber elements, the physical elements, and then make this co-simulation. This is what I showed before. This is what we want to enable with the orchestration engine to make these perform. And then when we have something that we actually can use, or we are satisfied with the models, we actually can both co-generate the real code and at the same time realize the real plant or this real physical system. And then we can actually do some testing. So yeah, and this is the other contribution, or at least where I will look at in the next year, to actually go from a model to code. Yeah, this is just so we will be able to do actually this, but actually with a lot of different tools, not only because this project, what make this actually couple two tools very closely together, but we can actually avoid this with the FMI standard by actually coupling all kinds of tools that are able to export this FMI standard. Yeah. Yeah. Yeah.
Are you actually going to develop any FMU or new software, or you will just be using the available FMUs for different case studies?
It depends. One part of it is we develop such a master algorithm, but we also have something called Overture, which is software, formal modeling of software. This is a tool developed here in AU. So we also make an export for FMUs from that.
Okay.
So it's actually two unrelated things, because the other one, actually just as soon as we have the FMUs, then we can make some co-simulation together with that.
But so you would do like the master algorithm in Overture?
Yeah, this is the thing we can currently do.
Okay, I didn't know that.
Yeah, and also a part of this is also that we want to see how that fits with the real industrial case studies. Because we find some limitations as something we need to change in both the standard and something they made optional. We actually see now it actually has to be mandatory. So it's also contributions with respect to that. But I just mentioned this because it's a more concrete project just to show something. But yeah, it's also part of research that we should see actually, does it work, or what do we need to actually, what does an FMU need to contain in order to make such a co-simulation? So that's part of it. But yeah, we also do export FMUs, but that's for our tool. We also support that, or want to support.
Yeah. I would like to know, actually, the question, I don't know if it fits well with the techniques that you actually study.
Yeah.
But I would like to know if, and whether it is possible, and how can we use these tools to study the performance of network protocols that could be very complex.
I think it depends on if you can export it as an FMU, then you can actually do it in connection with other tools that maybe describe something else.
For example, can we imagine as different layers of the network and tasks that are performed in each layer as kind of FMU, and then these techniques can be used to co-simulate
because when I did an stay abroad now, and I was, we were doing like some co-simulation using like the FMU and FMI standards as well. And one of the FMUs, like the functional mockup units, one of the simulators that we were coupling was Omnet++. So there in Omnet++ you can put whatever you want. You just create your model, and the FMU is able to interact with an Omnet++ simulator. So you could have, I don't know, MATLAB or Python interacting with an Omnet++ model in a simulation environment.
So, you know if for example, the normal classic approach to evaluate the performance of, for example, if they propose a network protocol, is this the same approach that they use, or, I mean, is it a classic approach to evaluate, because they are very, very complex, and you, for example,
I really don't know.
But yeah, basically what you will use this for is to couple different kind of tools. But if you can do this, what you say, already in one tool, then it doesn't make sense. But this is more to couple across tools. You know? So if you want to couple across different tools to see how different components connected together do in a whole system, you know, this is more for that.
About the synthesis side, when you go from model to code,
Yeah.
as I see you consider the structural part of your model. What about the behavioral side, like you have some operations or methods, then also do you consider this, like combine them and synthesize them into the correct entities of classes, or you just put them as a code at the end? So, how is this handled?
Yeah, so we use this, what we will code generate, at least in AU here, is going from this formal model of a VDM to C code or C++ code. And then we let the rest go from like a standard compiler to executable code.
Okay, so you don't model the behavioral side.
What do you mean outside? The environment
The behavior
of what?
of your model, like you have some functions, like this, some complexity inside, like to do some operations. So you have like, for instance, like some function calls to get some data and perform some computational analysis.
But that's just part of inside the code here.
Okay.
You know, this is just a model where you describe how you want the system, what you want it to do. It can be any source of algorithm. You know, here, you know, when something happens and according to the software you described, it just does that, and then it performs the output. But of course, like I said, one of the key challenges is when going from a simulation to the real thing is actually time, because time is actually introduced in software when you put it on a platform, and the way you implement it. So this is what we'll be looking at in the next years. Right now we code our case studies want to use. So that kind of thing will just be part of this code, will just be generated to code. Yeah.
When you do these code simulations, you also have the interfaces between the physical side and your code. Have you done any considerations on how you should port this kind of communication? Because you generally do some kind of abstractions on that also in your code simulation models.
You mean input, output, or?
Input, output, like, let's say an output, and normally it's just a value in the code simulation, but in reality it's a PVM generator that's running.
Yeah. So these are some of the challenges we will address. Currently we don't have any specific solutions, but this is also one of the problems. Not the problems, but one of the challenges is also how we actually put such inputs and outputs in VDM models. We actually want maybe to do a little bit different than DESEX did. Something like having a fixed address in a public static address, like it's in the real implementation.
Yes.
So we are considering that, but that's not currently. But that will be, of course, part of the future work. Output generation here.
Any final questions?